Greetings and welcome to my channel. I'm Mr. D and today we'll be discussing the atom. Atoms are incredibly small. Comparing an atom to an apple size would be like comparing this apple to the size of the Earth. The largest atom is 5.4 times 10 to the negative 10 meters in diameter. That's a decimal followed by 9 zeros and then 5 and 4. It would take 18 million of these atoms to span the diameter of just your pinky. Now you might think that the idea of the atom is a relatively recent development, but you would be wrong. The idea that stuff is made of little tiny particles actually dates back to the 5th century Greek philosophers Leucippus and Democritus. They said that all matter is composed of minute particles. They gave these particles the name atomos, which is derived from the Greek word for indivisible. Aristotle, a more prominent philosopher, believed that everything was made up of different combinations of 4 elements: earth, air, fire, and water. He said these elements were infinitely divisible. To these philosophers, elements and atoms were philosophical concepts, and as a result, there were no experiments performed to test these ideas. Due to Aristotle's prominence, his ideas held sway for over 2,000 years. In 1803, coincidentally the same year as Louisiana Purchase, an English school teacher by the name of John Dalton challenged Aristotle's ideas. He revolutionized chemistry by saying that the behavior of matter can be explained by his atomic theory. His theory was composed of 4 parts. All matter is composed of minute, indivisible particles, called atoms, and atoms are the smallest unit involved in chemical changes. Atoms of the same element have exactly the same mass, size, and other properties, and they were different from atoms of other elements. Compounds of 2 or more atoms of different elements combined in definite whole number ratios. In a particular compound, these ratios were always the same. Atoms are neither created nor destroyed during chemical reactions, but are rearranged, separated, or combined to produce substances with different properties from those with which you started. His ideas were largely accepted by the scientific community, and to a large extent have stood the test of time. However, as we've learned more as science has progressed, 3 revisions had to be made. Atoms are indeed divisible. They are made of still smaller particles, and we'll talk about those in a future video. Atoms of the same element do not have all the same mass, and we'll talk about these as well. All atoms of an element are chemically the same, and atoms of different elements are chemically different. Although atoms can't be created or destroyed during chemical changes, this can happen during nuclear changes. This would be nuclear fusion and nuclear fission. I want to talk next about the different atomic models leading up to the one we have today. But first we need to talk about what a scientific model is. A scientific model is a representation of something that is too small to be seen, something is too large to be seen in its entirety, an idea, a system, or a process. The model can be a diagram, like a wall map or a chart showing the Earth's water cycle, a physical model, like a globe or a plastic human torso showing the internal organs, a mathematical equation, or a computer simulation, like weather departments use for forecasting the weather and predicting the path of a hurricane. In late 18th and early 19th centuries, there were people who believed the idea of atoms. But keep in mind, many only thought there were 4 elements. They thought the thing that gave the elements their properties were their shapes. So for instance, particles of fire had sharp, jagged edges, and water particles were smooth and rounded. John Dalton, who we met earlier, was an avid fan of science, and as such he subscribed to different scientific journals. It was through his study of these journals and his somewhat poorly executed experiments, he was a bit of a klutz, that he learned about the different elements that we know of today, and how he came up with his all-important atomic theory. Dalton's model of the atom was that they were smooth, solid spheres like a cue ball in billiards. It took a while for this model to be revised, but it was in 1904. In 1897, English physicist J.J. Thomson was experimenting with a device which came to be known as a cathode ray tube. It's basically a sealed glass tube that's had most of the air removed from it. It's a positively charged electrode on one end and a negatively charged electrode on the other end. When the current is turned on, he saw a beam extending between the 2 electrodes. Through experimentation, he discovered that the beam could be deflected using magnetic fields and electrically charged plates. Since the beam appeared to be attracted to the positively charged plate, known in science as the cathode, he called the beam a cathode ray. Hence, the tube became known as a cathode ray tube. Because the beam was repelled by a negative charge and attracted to a positive charge, Thomson proposed that the ray was composed of negatively charged particles, which we've come to call electrons. He further hypothesized that these particles came from atoms of the electrodes. Because the beam was repelled by a negative charge and attracted to a positive charge, Thomson proposed that the ray was composed of negatively charged particles, which he came to call electrons. He further hypothesized that these particles came from the atoms of the electrodes. The discovery of the electron by Thomson required an update to Dalton's billiard ball model. Thomson's model was called the plum pudding model. You can think of this model as being like a blueberry muffin, with the cake part of the muffin being positively charged part of the atom evenly spread throughout the atom, and the electrons were scattered within it, like the blueberries randomly scattered within the muffin. The model of the atom was revised further in 1911 by Ernest Rutherford, based on his now famous gold foil experiment. You can click on a link below in the description to learn more about how this experiment works, but here are the basics. He put a radioactive substance, radium, in a lead-lined box with a tiny hole in it. Radium releases positively charged particles, called alpha particles, as it undergoes radioactive decay. The hole in the box allowed him to create a beam of alpha particles, which he aimed at the extremely thin film of gold foil. He surrounded the gold foil with a screen that would fluoresce, glow, when struck by the alpha particles. Rutherford expected that since the positive charge of the gold atoms was spread throughout the atoms, the beam would barrel right through the atoms and strike only the back of the screen. Although most of the alpha particles did indeed make it through the foil to strike the screen behind the foil, there were also periodic strikes to other parts of the screen as well. Much to his surprise, some of the alpha particles actually appeared to have bounced almost completely backwards. He said he couldn't have been more surprised if he had shot an artillery shell at a piece of tissue paper and it came back and hit him. That's how unexpected these results were. He had to find a way to account for this. He had to update the model of the atom. In order for the alpha particles to have been deflected to the side or to have been bounced back the way they did, instead of the positive charge being evenly spread throughout the atom, the positive charge must have been concentrated into a dense core in the center of the atom. The electrons were found swarming around it in a vast, empty space surrounding the positively charged nucleus. This is the nuclear model of the atom, and while it did advance the model of the atom and explain the results of his experiment, it failed to provide much information about the atom's structure with regards to where you find the electrons. This brings us to 1915 and the work of Niels Bohr. Bohr gave us what we can call the planetary model of the atom. He said the electrons orbit the nucleus in fixed patterns, which we refer to as energy levels, like planets orbiting the sun. Electrons closer to the nucleus required less energy than the electrons that orbited further away. Bohr hypothesized that electrons lost or gained energy by moving between energy levels. Just like a ladder has rungs that are a certain distance apart and require more energy the higher up you go, electrons require discrete amounts of energy to move further away from the nucleus. Just like you can't step between the rungs to climb a ladder, electrons can only move from one energy level to another energy level. Not enough energy or too much energy, and the electron won't move to the desired energy level. A discrete amount of energy, like this, is known as a quantum, the plural being quanta. We say that these specific amounts of energy are quantized, and each element has its own unique set of quanta that are used to identify it. In 1927, scientists had developed what we call the quantum mechanical model of the atom, which is built on Bohr's work and explains why electrons don't lose energy and fall into the nucleus. In this model, the electrons aren't in fixed orbits, but rather move within the atom within certain regions. We can mathematically predict where an electron will be within the atom. Each prediction can be represented by a dot. All of these dots together make up a cloud that represents the probability of finding the electron around the nucleus. The denser the points, the greater the likelihood that you will find the electron within a region. The less densely packed the points are, the less likely you are to find the electron, but you know it'll be somewhere in there. It's just like the blades of a spinning fan. You can't say at any given moment where any of the blades are, but you know if you stick your finger into that blur, your finger's going to get hit. This three-dimensional cloud of probability points is what we call the electron cloud model. It's a mental model of where in the atom the electrons can be found. There's a minute physics link in the description below where you can learn a little more and see some of the electron clouds visualized. Biographical endnote. John Dalton was an English school teacher born in 1766 who developed an intense interest in science. He started his teaching career at the young age of 12 and was also around this time that his interest in science developed. Initially, he was drawn to meteorology, which he studied using instruments of his own construction. In time, he moved on to chemistry, but never completely gave up on meteorology, making daily observations in his weather diary until the day he died. He's the first person to publish a paper on color blindness in 1794, being interested in the topic because both he and his brother were colorblind. His interest in meteorology led him to study air and the property of gases, which got him supposing that gases were made of tiny particles, just as both Robert Boyle and Isaac Newton believed. This led him to his law of partial pressures in 1801. He began to consider that all matter, not just gases, may be composed of tiny particles. Proust's work in 1788 on his law of definite proportions was firmed up by this idea and led to Dalton's later law of multiple proportions in 1803. Because of his broad interests and the fact that he wasn't concentrating on one aspect of atoms in chemistry, he was able to see how the work being done by others were interrelated in a way that others did not. Between his own experiments, poorly performed as they were, and the work of the scientists of his day, he brought together all the disparate ideas about atoms and created his groundbreaking atomic theory. Additionally, he was the first person to create a table of atomic weights. For a self-trained English teacher, John Dalton left an amazing legacy of science. Thank you for watching my video. I hope you found it both informative and interesting. If you did, please smash that like button below and consider subscribing and hitting the notification bell so you know when my next video comes out. When it does, please join me again. Until then, be good, be careful, and don't trust atoms. They make things up.